Hey everyone, this is Michael and Miriam Snoyman. We are going to be going through section 10 of the FP Complete Rust Beginners course. This section is on pointer types and interior mutability. I have a lot of trouble saying that word. Anyway, we're going to be going through this together. This is Miriam's first time seeing the material outside of 5 minutes earlier today before our son got in the way. So we're going to be going through this. Hopefully Miriam will be asking some questions that a lot of you will be asking. Hope this is helpful. All right. So quick recap before we dive in. There are 3 different parts of memory. And this is going to be relevant to what we're dealing with later. 3 parts of memory are program memory, which is read-only. The most common thing you see stored there is string literals. You can have a pointer into that space, but you can't change things there. You can't create things there. The stack is where all variables are stored. Everything that gets stored on the stack has to be sized. So that means based off of the type, we know exactly how much memory this thing is going to take up. And then there's the heap, which allows dynamically sized types. It allows things which may take up more or less space, and access to it is slower. In addition to that, you have to manually manage the memory. Except Rust does a lot of that automatically via the drop rules, the ownership rules. Mm-hmm. Okay, I think that's enough. Let's dive in and see our first pointer type. So a box. And we're going to just go ahead and copy this over to our code and start playing around with it. This here, this x variable, it's going to live on the stack. So U32, it's going to take up 4 bytes, and it's holding on to the 5. That value 5 is sitting directly there on the stack. No surprises. Y is holding on to an array of 5 U32s. Now, a U32 has a known size, 4 bytes. 5 is a known number. 4 times 5 takes up 20 bytes. Therefore, this is not a dynamically sized type. Even though it's an array type, array types are in fact sized in Rust. Mm-hmm. So we're able to store those values directly on the stack. Vec is the most interesting of these 3. A vec allows you to store a dynamic number of values. So we're going ahead and creating this one with 5 values in it, but we could just as easily add more values to it going forward if we made this mutable. The vec still lives on the stack. It's pointing to memory that's stored on the heap, but the value itself, the vec itself, the pointer into that piece of memory, all of that is staying on the stack. So the vec itself is statically sized, mm-hmm. even though the value inside of it, morally, theoretically, that value is in fact dynamically sized. Mm-hmm. Cool, so all of those work. The first one that doesn't work, though, is storing a slice right here. When you have a slice of U32, you can't see from the type how much space it's going to take up. We know that each U32 is going to be 4 bytes, but we don't know how many of them there are. Mm-hmm. So if we tried to borrow that vec and then dereference it into a slice, we end up getting some errors. Both of these are the same. Well, this one's not exactly the same. Ignore that one for the moment. This is the interesting one. You cannot know at compile time the size. So how do you hold on to a slice? Mm-hmm. One answer would be you can't. One answer would be you can hold a vec, you can hold an array, but you can never hold a slice directly. You can have a reference to a slice. That's not entirely true. One way to do this is with a box, and this is our first pointer type. In the same way you can hold a reference to this slice and everything is fine, you can have a box, which is now an owned reference, so to say, to this slice. This box is now holding on to the memory. It's owning the memory. Mm-hmm. When this box goes out of scope, it's automatically going to drop that value. It's going to free the memory. Okay. And this is allowed. Similarly, you can take just any number, which, like the number 6, which is a U32, and also store it in a box. This isn't necessary. You don't get any advantage in this case by storing the number in a box instead of storing it directly on the stack.
Because it's already sized, so it's just extra layers.
Exactly. Okay. It's a layer of indirection that we don't need. There are some cases where you may want to stick something like that in a box. That's not the important part here. Okay. But this is actually allowing us to do something that we've never really done before. Directly hold on to a slice. Okay. Let's see another example of a dynamically sized type. We have this trait, std error error. This is a superclass. It's like a superclass. The trait for everything which may be an error. So it could be for the stdio error. Maybe you're using something like Tokyo. Maybe there's some kind of error type in there. Maybe you're using the hyperlibrary or request or something like that. And each one, or Serde, each one of these defines their own error types. How big is the error type?
Well, you don't know.
You don't know. Saying I have something which implements this trait is dynamically sized. So if I want to be able to, we're going to see this now, I want to be able to return a value which implements some kind of a trait, but I don't know what kind of a trait it is. I can't do it directly. So the trick, the approach, is you wrap it up in a box. So now what you're able to say is, essentially what you're saying is, I'm going to take some error value, I'm going to stick it on the heap, I'm going to hold a pointer to that.
Okay.
The box is going to be the pointer to that.
Okay.
The box knows how to drop that. And then I'm able to access this through the interface provided by this trait. This is different than impl_trait. With impl_trait, we know at compile time what type is going to be there. But you can see here in this example, we don't actually know what's going to be here. At least from the, we could analyze the code. But looking at this code right here, we've got first thing, which returns a my error 1. And second thing, which returns a my error 2. Now we can look at this code and we can see first thing actually fails, and therefore this is going to return a my error 1. But I can just as easily change this to be okay. And now a different value is going to end up there. Or we could have it based off of a random number generator or some input from the user or something.
Right.
So the point is we don't know at compile time exactly what type is going to end up there. So this is
But
one.
box lets us do it.
Exactly.
Okay.
Box lets you package up anything in there.
Okay.
Down here is just implementation stuff to make this work. Nothing terribly interesting. Okay, so that's a primary example. Now, let's see another motivation for when you would want to have some kind of a pointer type. Here we go, going back to a person. This time we've got a first name and a last name. And because it's convenient, we're going to use owned strings.
Okay.
We're not going to use string slices. That would require lifetime parameters. That's always a pain. So we have an owned string for the first name and an owned string for the last name. Now we're going to have Alice Smith and Bob Smith.
Okay.
Alice to string, no problem at all. That makes perfect sense. Bob to string, no problem at all. And Smith. Smith.toString, no problem.
Okay.
The one thing that really irks me is this line here. Last name is Smith.clone. And we have to clone Smith because otherwise Alice and Bob are going to own the same string. They can't both own the same string. That's not allowed according to the ownership rules. Make sense?
Yeah.
So this is one way of solving the problem, just wasteful cloning. That's fine. And in an example like this, I'd probably just do this because the overhead really isn't that bad. But it is wasteful, and when you get to larger programs, then this is not a good choice.
Okay.
So, how can you work around this? Reference counting. There's no garbage collection in Rust. You can't say, I'm going to create a value, and I just want you to clean it up when everyone's done with it. You can't just do that generally. Reference counting is a trick that lets us do that. Every time someone owns a reference to this, they increment a counter.
Okay.
Every time they drop it, they decrement the counter. And when the counter goes down to 0, then the last person shuts off the lights and drops it. Make sense?
Yeah.
All right. So, reference counting. This has to be heap stored. If you stored it on the stack, now it's just not going to work with the way that the stack works. So you have to store these values on the heap so that it doesn't follow the linear lifetimes of all these different pieces of the code. So it lives on the heap. But unlike a box, which just has one owner, a reference counter is going to maintain an additional piece of data saying how many owners are there.
Okay.
Okay. And finally, it gets dropped when all the references are gone. We are going to still, here, we're going to look at the code now. We're still going to end up using clone like we did previously. And that feels dirty to some extent, except it's not. This clone here, previously, when we were cloning the string directly, that means that you have to allocate a block of memory and you have to copy all the values and then you have to deallocate all the memory. when we do a clone on an RC, which I'll show you in a sec, when we do a clone on an RC, all that ends up happening is we increment a counter.
Mm-hmm.
That's very cheap. All right, so let's check out the changes. We had to use the RC type,
Okay.
which comes from std rc rc, RC standing for reference counted. First name remained the same. We could wrap this in an RC as well, but we were doing an example that all the first names were different, only the
Right.
last names were shared.
Yeah.
Now we have last name is going to be an RC of string. It's parameterized. Obviously, you can put other things there. We're just putting a string here this time. And then in order to create an RC, what we're going to do is we're going to do RC new and provide it with the Smith.
Okay.
You could also, if I remember correctly, you can also use dot
RC.
into.
Oh.
Maybe I'm wrong. Let's see. Oh, I was right. It just needs a little bit more type inference help.
Mm-hmm.
Personally, I like being explicit about this. Go RC new. That's fine. And then we're able to clone it and then move it in over here.
Okay.
And everything works.
Yeah.
Make sense?
Yeah, it's very reminiscent of how the borrow checker works.
Exactly. In many
Where
ways,
it keeps track of all the references, keeps track of all the borrows, and then when all the borrows have gone out of scope or dropped or whatever, then it's done.
yes, it is very similar to that, although the next thing is going to be even more similar to that.
Okay.
Not the next one, the one after that. Okay. Interior immutability. This is an orthogonal concept to the pointer types, but the two of them end up going together so often that it's worth covering them together.
Mm-hmm.
Interior immutability allows us to cheat the rules of mutability. Every type in Rust, every struct in Rust, determines the mutability of the values inside of it. If you have a person and the variable holding that person is immutable, the fields inside of it are immutable too.
Right.
However, every once in a while, for various reasons, we want to cheat and we want to pretend like something is immutable, but still be allowed to mutate things inside of it. That's where interior immutability comes in.
Okay.
And the basic idea is that we are now moving from letting the borrow checker check all of our mutability rules to doing it at runtime. We'll see what that looks like. Cell is the first example we're going to see. Sorry, the important line here is actually the one I just skipped. Allow multiple references to mutate. That's the thing that the borrow checker typically doesn't allow.
Mm-hmm.
If you have multiple references, they all have to be shared references. They have to be immutable references.
Mm-hmm.
However, if you go ahead and you use interior immutability, you can have lots of different things that are all referencing the same thing. They have shared references, immutable references, but they can go behind the cell and start mutating things.
So this is so we're getting around the you can't mutate after borrow issue.
Correct.
With this?
Exactly. So the cell is the first one we're going to see. And so I'm going to make the font just a little smaller. Okay. So the example we're going to have here is logged access. Let's say we've got a value, string. We want to know how many times the value has been peeked at.
Mm-hmm.
How many times it's been borrowed.
Okay.
So we have this value and we have a counter. And instead of just putting it as a uCell, we're going to use a cell. Sorry, instead of just a usize, we're going to have a cell of usize.
Okay.
Creating a new value, a new logged access, you give it the value, and then you create this. Counter starts off cell new 0.
Mm-hmm.
Nothing terribly surprising there. Let's check out borrow value. Now notice, we have an immutable reference to self.
Right.
So we can't mutate it at all. That's banned. The borrow checker will stop us.
Mm-hmm.
We want to return a reference to the string. So the first thing we're going to do is self.counter.get. This is a method on cells.
Mm-hmm.
We're going to get the original value that was sitting inside the cell. That's not mutating. That's fine.
Okay.
This next line is the interesting one. Line 16. We're setting a new value.
Oh.
Even though we have an immutable reference to self. So we have an immutable reference to this logged access.
Mm-hmm.
And therefore we have an immutable reference to this cell. Even so, cell provides us the ability to mutate things. And actually, go ahead and pop over to the documentation, we can see this in action. If we jump down here to set, notice that set is taking an immutable reference as its first parameter. So it explicitly is designed to work on something immutable, even though it's mutating.
Huh.
Under the surface, it's doing unsafe things to make all of this happen.
Right. And this is explicitly just for cell. It's not
correct
everywhere.
Correct. This is, in some ways, you could consider this opt-in. This is opt-in breaking of the rules.
Right. But it's containerized.
Correct.
So it's more or less safe.
Right. Or at least it tells you what part of your code to stare at when you want to see what could be broken. Oh, shoot, I have a race condition.Maybe I should go look at that place where I turned off the safety rails.
Right.
Okay.
I was going to ask you about race conditions.
This actually does provide the possibility of race conditions. One thing to point out about this, and it's relevant, returns a copy of contained value. Notice up here in the signature of this impl, T has to be a copy value. Because when you call get, you haven't invalidated the cell. There's a value sitting inside the cell, and you've gotten another value, not a reference to the value. You've gotten a brand new value outside. This only, if you think about ownership rules in Rust, this only works if you can freely copy the value. So you can't stick a string inside the cell, because a string can't be copied. So cell works very nicely for a usize. It works very nicely for anything that can be copied under certain circumstances, but it doesn't work in general for other types. Okay?
Okay.
But anyway, let's pop back over here. So borrow value, we set the new value, and then we can just return a reference. Again, we're back to normal safe Rust code. No weird mutability stuff going on. Down here, I've implemented a drop just so that you can see in practice how that the counter has been incremented. And then the main function, we create a new logged access and we iterate over it 10 times. And if I run this, I actually have to save the code before I run it. That's one of the tricky things about writing Rust code. You have to be not stupid. Okay. But then dropping after 10 accesses. Okay. Does this make sense? Do you have any questions?
No, it makes sense.
Okay. Cool. So that's basic interior immutability. The next one is RefCell. Let's say we want to be a little bit more sophisticated. Instead of just storing how many times we've accessed it, maybe we're going to have an audit log, an audit trail. And each user who's requested access to this file, to this thing, we're going to go ahead and append their name to a vec.
Okay.
That would make sense.
So we have a list of who accessed it.
Exactly.
All right.
You can't really stick a vec inside a cell. It works up here. Well, now this type mismatch is fine. So I'll do vec new to start off. And that works. But now down here, we're going to change borrow value to also take in a string of the borrower.
Okay.
Immediately we get to this line and we have a problem. Let's look at the problem. No method named get found for cell. But we saw that already. Look very carefully. The method get exists, but the following trait bounds were not satisfied.
No copy.
No copy. You can't grab the vec that was inside of it. It's not allowed. Instead, what we'd like to be able to do is get a reference to the vec inside of it and then mutate that. And as soon as we cross that line, we're no longer talking about a cell. We're talking about a ref cell. So we're going to go ahead and change this to a ref cell. We're going to change this to a ref cell. Odds are pretty good that pretty soon I'm going to make a mistake in the code I'm writing and I'm going to have to copy paste. We're going to see how far we're able to get. All right. So, and we're going to call this, instead of counter, we're going to call this audit log to be consistent with the code over there, because this isn't a counter anymore. All right. So now we're going to do self.auditLog.borrowMute. This is just like using the mutable borrow operator.
Okay.
Except it's a method on a ref cell.
Okay.
And now we're going to do .push borrower. Because push on a vec requires a mutable reference. We now have a mutable reference. We'll look at the type in a little bit because it's very interesting what that type is doing. We can get rid of this bit here. And now we're going to go ahead and, how did I test this thing? Well, let's just go ahead and copy the rest of it because it's not terribly interesting. We're going to have a drop that prints out the full audit log. And then our main function is going to borrow the value with Alice, Bob, Alice, and then Charlie.
Okay.
If I run that, you can see that it's actually populating that vec.
Mm-hmm.
All right. So now let's go ahead and have a look. Actually, let me peek at the next one. Yeah. Let's go ahead and violate things first. We have borrow checker rules. The borrow checker rules say that you cannot have a mutable and an immutable reference at the same time, correct?
Right.
What happens if I try to do that with this RefCell? What if I try to borrow something and immutably borrow it, and mutably and immutably at the same time? Is the code going to compile? Let's find out. I'm going to go ahead and pull in this bit of code.
You would think it wouldn't compile. You would think that.
You would hope that, but that's not the case. The compiler's not smart enough for that. And we'll see why. Let's go ahead and see this code. So we have a RefCell holding onto a string. Okay?
Mm-hmm.
We're going to borrow mute. Now, when you just do a normal mute like this,
Mm-hmm.
it gives you back a mutable reference. You can't do that here. Instead, borrow mute gives you, here actually, let me pull up the documentation. Borrow mute gives you back this special type, refmute.
Okay.
Refmute is another kind of let's look at the documentation. It's a wrapper type. It acts just like a mutable reference, except it's special cased for a RefCell. The reason why this thing exists is to enforce invariance. It's going to keep track that something has borrowed the RefCell mutably. Mm-hmm. So when I go ahead and I do borrow mute on this, I am now holding on to this thing called a refmute. I own it. Mm-hmm. And it has somewhere inside the RefCell marked off, hey, someone has mutably borrowed this. Here, I'm going to go ahead and borrow. Now notice that these two things are both alive at the same time.
Right.
X and Y. So value is, and I'm going to use Y. Then I'm going to deref X to be able to mutate the value inside of it, see the value. Now this code actually compiles.
Okay.
Let's see what happens when we run it.
Already immutably borrowed.
What RefCell does is it moves the borrow check rules from compile time
to runtime.
Exactly.
This may be a stupid question. What if we switch these? If the non-mutable one, if the immutable one was first, would it make a difference?
So pay attention to the error message very carefully.
Okay.
Already mutably borrowed. Okay. Mm-hmm. Let's go ahead and try that again.
Already borrowed.
Already borrowed.
Just not mutably.
Not mutably. So what's happened is we've already borrowed it here.
Hey, kiddo.
Hey, Lavi. Lavi, did you come to say hi to everybody again?
We're doing our work. You want to come see?
Lavi is going to learn Rust today. Okay.
You can say hi. You can say hi. Okay, now you can see.
Okay, we've recovered from the baby interruption. All right. Miriam, back to you. Okay. So,
where were we?
We were trying to figure out, can you see a way that we could try to fix this code so that it actually not only compiles, but it runs?
No.
Okay, so you had an idea before. You said, could we swap the order of this?
Mm-hmm.
Why did you think swapping the order might help?
I'm not sure.
Okay.
It was just a gut feeling.
So it was a very good intuition. Let's look through this. Line 6.
Wait.
Go ahead.
You can't mutate something if it's been borrowed elsewhere.
Correct.
So if we put the mutating one first, then it's a non-issue because it's already been changed. You're not changing it again.
Well, well, sort of. Not exactly correct.
Mm-hmm.
We're still holding on to the ability to mutate it.
Right.
All right. Let's step through this. Line 6, we're doing an immutable borrow.
Mm-hmm.
That marks off somewhere in the RefCell that something is borrowing this value.
Mm-hmm.
When does that mark go away?
When you drop the borrow. When it goes out of scope.
Yes, both of them the same thing.
Right.
When this thing gets dropped.
Okay.
Now, right now, when does Y get dropped?
Y gets dropped after line 9, after the println macro.
No. It looks like it, but it doesn't. That's the last time it's used. How long is Y? What is the actual scope? Well, here, let's pretend for the moment that you're right.
Okay.
Because this will help.
Mm-hmm.
If that was the case, and Y goes out of scope here and Y is dropped here,
mm-hmm.
Tell me how you would fix this program.
I would move the let Mutex to line 9 now, to after the print.
Okay, cool. So now we've done an immutable borrow.
Right.
We've used it, then we never use it again.
Right.
And then we do a mutable borrow, we mutate, and now the two of them don't overlap.
Right.
Almost completely correct. But if I run this, it still gives an error. Now this is, you're 95% of the way there, and there's a good reason for you to be confused about this.
Mm-hmm.
If these were normal references, then there's something called nonlinear lifetimes in the compiler. Mm-hmm. And that means that the reference would in fact go out of scope.
Okay.
And this code would compile. However, when it comes to actual objects, actual values, to follow the normal ownership rules, they only get dropped when they actually go out of scope, or when they're moved, or when you explicitly drop them.
Okay.
So there are two straightforward, I'm putting that in scare quotes,
mm-hmm.
there are two straightforward ways you can make this code run without panicking.
Okay.
You want me to show you both of them?
Yeah.
The first is to explicitly drop the Y as soon as we're done with it.
Okay.
That's by calling drop on Y.
Mm-hmm.
Now, Y has gone out of scope. Y has been moved into this function.
Mm-hmm.
When that function is done, Y no longer exists. Therefore, this value, the ref, gets dropped.
And it's done.
And therefore, it goes to the RefCell and says, hey, this thing is no longer being used, and borrowing it mutably is now completely safe.
Mm-hmm.
And that works. This is probably the approach that I like
mm-hmm.
the most, because I really like the explicitness of calling drop. Another method is by wrapping it
in a block.
In its own block. So now it has its own scope,
uh-huh.
and it goes out of scope at this point.
Yeah.
Okay.
I forgot about the block trick.
Make sense?
Yeah.
Okay. Cool. Any other?
No, that's cool.
Okay. Now, just one other point. You don't really need to have both an X and a Y here. You can do X, and then you could just
drop X.
You can just read from the X. You can read from the X and mutate through the X. It wasn't really necessary. This was a contrived example. Everything about this is contrived. But that is another point, just in case anyone watching this video is wondering why I didn't do it that way. Okay. We didn't do it that way because I'm trying to contrive an issue that doesn't exist. Okay. Cool. All right. So spawning threads. We haven't actually looked at spawning threads. As much as multi-threaded programming is terrifying and so complicated, it's actually pretty straightforward to get started in Rust. We're going to pull in two functions. Sleep. You give it a duration, and it sleeps for that amount of time. Spawn. You give it a closure. You give it a function that it's going to run in that child thread, and then it runs it in that child thread, and it gives you back a join handle so that you can wait. You can join the child thread to this thread, so you can wait for it to complete.
Okay.
All right? That's the whole API. Lots of complications built on top of that. Lots of other things. But the basics of multi-threaded programming in Rust, right there, that function. All right, so we're going to go ahead and create a mutable vector to hold on to all of the child threads, or the join handles for those child threads. Now we're going to iterate I is going to be everything from 1 to 10, or 11 exclusive. We are going to print starting thread 1, 2, 3. We're going to sleep for 100, then 200, then 300 milliseconds. Print a finishing message. And that's what we're going to do in the child thread. We grab the handle out of that, and we push that handle onto the vec of handles that we're waiting for. And then to make sure that all the child threads have a chance to complete, in the main thread, we go ahead and join all those threads, and only after all of them have completed, we exit the program. Without this, the program will exit immediately.
Okay.
So let's go ahead and run this. Okay, cool. So starting threads 1 through 10 prints immediately because these are in other threads. The sleeping means that these things get delayed a little bit more. They come in order, and then we're done.
Okay.
All right. No, there were no pointer types here. This is just setting the stage. Mutable state is the thing that makes concurrency difficult. The fact that you can have multiple different threads all trying to not only read a value, but write it, modify it at the same time. And that's what really causes a huge amount of problems. This is where Rust's fearless concurrency concept comes into play, and it has everything to do with, well, actually a large part to do with these pointer types. Let's see how. We're going to start off with this bit of code because we want to be able to share mutable state across multiple threads. I want to know how many threads are still active. So I'm going to create a mutable variable called count, set it equal to 0. And then in each of the child threads, I'm going to increment count. I'm going to do my starting print, and I'm also going to say how many other threads there are. I'm going to do my sleeping, I'm going to decrement it, and then I'm going to print my finish. Okay? Without thinking hard, just guessing at what the intent is, what do you think the output of this program is going to be?
More or less what we had previously.
What are the counts going to be?
It'll increment. The more threads are running, the more the count will be.
Right, that would make sense.
Yeah.
So it's going to say 1, 2, 3, 4, up to 10.
Yeah.
And then it's going to go down 10, 9, 8, 7, 6.
Yeah.
Or 9, 8, 7, 6 until it gets to 0. That's what you would expect. That's what we kind of want it to do, right?
Yeah.
Let's watch what actually happens.
Huh.
Every one of them is 1 until every one of them is 0.
Okay.
So here, everything is 1. Here, everything is 0. Why? This is complicated, by the way. This is tricky. It's not so complicated. It's obvious once I show it to you, but it's tricky. Actually, it's not even obvious once I point it out to you. It's a tricky one.
I mean, looking at the order of the code, it seems like it should still be incrementing it. It's like it's not looping.
No.
Or is it somehow like incrementing and decrementing it each time?
No.
Okay.
You see how I put in this word move?
Yeah.
Keyword move. What happens? So I've created in the parent thread, I've created this value, this variable count. What I want to be doing is I want to be mutating the same variable count, the same piece of memory through all of these. But I can't do that. If I take off move, I'm going to get an error message. Cannot borrow count as mutable more than once at a time. I can't have 10 threads all mutably borrowing the same variable. That's not allowed.
Okay.
That makes sense, right?
Yeah.
We'd also run into lifetime issues, but that's a different issue. We just, in fact, closure may outlive current. Okay, fine. That's going to get into other issues. So an easy way to solve this that doesn't solve anything at all is to put move here. Now the closure, instead of having a reference to this variable sitting outside of itself, we're going to move this variable into the closure.
Okay.
Since count is usize, and since a usize can be copied, it's going to make 10 copies of this variable, of this value. Each closure has its own copy.
So it's only ever getting incremented the first time.
So it starts at 0 in each thread. It gets incremented by 1 in each thread and decremented by 1 in each thread.
Okay.
So that's not the problem. So now we've seen we've seen this code compiles but doesn't do what we want.
Mm-hmm.
And without the move,
it doesn't work.
It doesn't work because you can't mutably borrow it multiple times, in addition to the lifetime issue.
Okay.
Okay. So what do we do? Let's try using an RC and a cell.
Okay.
An RC is a reference counter, so we could have multiple things. So the cell allows interior immutability, and the RC allows you to have multiple things all referencing the same thing.
Yeah.
That seems perfect, right?
Yeah.
So now we're going to have multiple threads all holding on to a clone of the RC. This is not going to work. Let's go ahead and implement it, though. So we're going to use RC. We're going to use cell. Now, instead of having mute here, we're going to have interior immutability. So we're going to say RC of cell of usize. And now instead of just 0, we're going to say RC new. Cell new. Okay.
Okay.
Cool. And now, instead, we are still going to move count in, but we need to clone it first.
Okay.
An RC is not copyable. So each time we iterate through this loop, we're going to create a new copy of count, which is going to increment the counter. And then that one can get moved into the closure.
Okay.
Now we have a new error message. Binary assignment operator cannot be applied to that. Okay, fine. Not a big deal. Let's go ahead and do this. Let count val equal count.get.
Okay.
Plus 1.
Okay.
That's the new value. Then we're going to do count.set count val. And then we're going to
do the opposite.
We have to do the opposite down below. That's true. Unfortunately, this doesn't work either. RC cell cannot be sent between threads safely. There's no reason you should know the answer to why this is happening. This is something I haven't shown you yet.
Okay.
An RC is a reference counted value. Value. It is not atomic, meaning it is using normal plus and minus operators, normal plus and minus machine instructions. If you have multiple threads all trying to add and subtract at the same time, they can trample all over each other. That would be a race condition. The compiler, and this is where fearless concurrency comes in, the compiler knows this. How exactly does it know this? That seems like an amazing thing for the compiler to know. Let's go ahead and look at RC. If I come down here to the trait implementations, you see how it says bang send?
Yeah.
Send is a trait. It's what's called a marker trait. It's a marker trait saying, I am allowed to share this safely between multiple threads. Not share this. I can send this from one thread to another. Why? Because there are certain invariants that have been respected. By putting the bang here, that's actually saying this is not true. This can never be true.
Okay.
An RC implement, in fact, you can look at the code. An RC explicitly says, I cannot be sent, and the reason is that the way that RC is implemented uses non-atomic increment and decrement. Cool. That's a lot of information, but the short answer is the compiler and the standard library are all working together to make sure you don't accidentally create a race condition.
Okay.
Now, fortunately, there is another pointer type built into the standard library called arc, atomic reference counted. Now, you might ask, why not just always use an arc? Well, it's because it's a little bit more expensive. Not significantly, but enough more expensive that we don't want to force it in every case.
So it would affect performance?
It would affect performance.
Okay.
So we can actually just come here and change out on our RC for an arc. Now this comes from the sync module, which is for synchronization primitives, useful synchronization primitives, meaning for multi-threaded code. Replace that with an arc, replace this with an arc.
Mommy, can Daddy share with me?
Yes.
With the brown fruit?
Yes.
Thanks.
Bye-bye. That was a short interruption.
It was.
Okay, so we replaced the RC with an arc, and that seems to fix things, except cells have the exact same problem.
Green paper.
Yeah, I know. And Mommy says you can have it.
cells have the exact same problem.
Okay.
So instead, for interior immutability, when we're dealing with concurrent programs, we can't use a cell. We could try to use a RefCell. In fact, I think that's the next thing. No, I didn't try it here. RefCell, you're going to run into the same issue.
Okay.
Instead, a Mutex is the right thing. The issue is we want to ensure that that we lock this value. We don't want anything else to be able to mutate it while we're working with it. So we can go ahead and replace our cell with a Mutex. Mutexes and arcs can both be sent to multiple threads, and sync means that that a value can be shared across multiple threads at the same time. So let's go ahead and replace our cell with a Mutex. Cell, put in the Mutex. Okay. Get is no longer something that we're allowed to use.
Because we're not using a cell.
Not using a cell. Get doesn't exist. Instead, get mute. Oh, interesting. I don't think I ever noticed that there's a get mute. I should have. Instead, the way that I've always done this in the past is we're going to go ahead and get a mutable lock. Locking the value can cause an error. This has to do with poisoning. It's a more complicated concept. Generally speaking, if your lock fails, then you just use unwrap and you panic and you kill the thread. Generally speaking, it means your program is screwed, no matter what. There are some cases where you could recover from it, but it almost never happens. So what we're going to do is we're going to go ahead and get a mutable Mutex guard. As long as this guard is in scope, as long as it's alive, we are holding the lock on this Mutex.
Okay.
Nothing else is able to lock it. So everything else will sit and wait until we're ready.
This is how we prevent the race conditions.
Exactly. Now we're going to do count plus equals 1. And then here we're going to dereference count. Okay. Now down here, let's get rid of that. We're going to do count minus equals 1. We're going to dereference count. And our program compiles again. Let's go ahead and run this and see if it does what we think it's going to do. Not exactly the behavior we were expecting, right?
Yeah.
Starting thread 1, finishing thread 1. Let's go back to the code and see why.
That has to do with the locking, because it's not allowing the next one to start before we've finished and unlocked it.
Exactly. That's exactly correct.
Okay.
You nailed it. We've grabbed the lock here on line 10. How long does count live? It's all the way to there.
Yeah, until we're done.
Where do we want to drop the lock?
We want to drop the lock after the first print call.
Exactly. So let's just go ahead and use std drop, stdmin drop. In the code that I put in the slide, it actually is using the braces, but we can just drop it like that. Now we run into a new issue. Borrow moved value count. So how do we solve that?
Copy?
Not copy. The issue is that our lock is gone.
Oh.
Which is exactly what we wanted.
Right.
We need to lock it.
We need to lock it again before we change it.
Exactly. Now we're actually just running into a variable name issue. So I'm just going to call this count Mutex, Mutex, because I shadowed the name count above. Now let's go ahead and run this thing. And finally,
it does what we want.
We have exactly the behavior we wanted. Okay, cool. Make sense?
Yeah.
Okay. There's another thing in addition to a Mutex called an RwLock, which doesn't really help us here, but it's a good one to know about. RwLock is a read-write lock. It means that multiple things can all have a read lock at the same time, kind of like shared references, but only one thing can have a write lock at a time.
Okay.
So if you have a piece of data that lots of threads all want to be able to read from, like a cache, for example. They all want to be reading from the cache, but every once in a while, one thread needs to write some data to it. An RwLock can be much more efficient than a Mutex. It doesn't apply in our case because we've got such a short window, and every single time we read it, we also write it at the same time.
I can definitely see that there would be application for that where you only want one thing, obviously, only want one thing to be able to change it at a time, but you've got a lot of things looking at it.
Right. Let's go ahead and check this out. I'm just going to modify this. It doesn't, again, this is not a performance boost. It may even be a performance problem, but I'm not sure. I'm not sure of that. So what I'm going to do is I'm going to count.write.unwrap plus equals 1. Now, the lock that we grabbed is a temporary. It doesn't get saved in a variable. It's temporary. It goes right there. Here, count.read.unwrap. Yeah, we can get rid of that. And now down here, we're going to do the exact opposite. Oh, and here. Oh, use variable. That's right. Just because I used the name variable, the name count again. All right. And it has the exact same behavior, the one that we wanted it to have. Make sense?
Yeah.
One final thing to point out, in addition to these actual locking values, some types, some primitives, especially USize, the numeric primitives, they provide, inside the standard library, there are atomic versions of them. The atomic versions of them allow you to make modifications, read things, write things safely without taking any kind of a lock. This is for lock-free implementations. All right, that was not the code I was trying to copy paste. So we've got std sync AtomicUsize. There are ordering issues. It has to do with memory barrier, which are things that are beyond my knowledge, my experience. This has to do with the way that processors deal with these atomic operations. Not expert enough at all to comment on this. So now instead of having a mutex of a usize, we just stored the AtomicUsize.
Okay.
We still need the arc because we need multiple things to be able to access it at the same time. It gets stored on the heap, etc., like before. And now, instead of locking, we have this specialized method, fetch add. We're saying we want to fetch it, add 1 to it. We use relaxed memory ordering. And then it returns the original value. The value before adding the 1, so we add 1 again to find out the new value.
Okay.
And we do the opposite down here. We do fetch sub.
Subtract. Yeah.
And now this is the I guess this is the most efficient version. Anyway, it's more efficient than the Mutex and RwLock most likely because it's not using any kind of locking. And it has the expected behavior.
Nice.
So caveats on threads. Spawning that we've done here creates a system thread, which is not great for high capacity servers. You can use spawn, you can use these direct threading capabilities for many programs, but if you're doing some really advanced stuff, that's where things like async, await, and Tokyo, which is a separate lesson, that's where those things come into play. All right, so here's the exercise, and I guess we'll just stop here because we're not going to do the exercise. Okay.